let's see, fine. Prime. F of x is equal to e to the x squared sine of 2x. All of that's up there in the exponent. X squared times sine of 2x is in the exponent. So in our chain rule, the first thing you see is the outer rule. So we're going to use the fact that the derivative with respect to x of e to a power is itself times the derivative of the power. That's our plan. Let me see if you can do it. So I hope you see when it's time to take the derivative of the exponent that you're going to use a product rule. So you always go for that partial credit. This will get you halfway there. That gets you halfway there. Derivative of e to a power is itself. And now we're going down here on the same line as the e, put the derivative of the exponent. Go with product rule. First times the derivative of the second, plus the second times the derivative of the first. Okay, so the first factor is an x squared. The second one is a sine function, and it's a sine of 2x, so it's a composite function. We start by taking the derivative of the sine function, and we get the cosine of that same angle, but now we have to go inside and take the derivative of that angle. And that's going to give us this 2 right here. So that's first times the derivative of the second. Now the other way, the sine of 2x times the derivative of the first, derivative of x squared is another 2x. And so I'm going to take that stuff inside here, and I'm going to make it look prettier by putting it in front of the e. And I'm going to put the 2 with the x squared. So I have 2x squared cosine of 2x. I'm going to put this in front of the trig function, plus 2x sine of 2x. And then I've got the exponential function as we started, e to the x squared sine of 2x. How was that for everybody? Able to take that kind of derivative? Everybody? All right, let's see if you can do something like this. So what's the big deal about this problem? How is that a chain rule other than the parentheses? The square means the whole trig function is squared. So it might be to your benefit to rewrite it, just to remind yourself that that's the outside rule, the squaring. So when you take the derivative, you start here. Bring the power down, raise this to 1 power less, then go inside and take the derivative of the stuff inside. I need to remind anybody what the derivative of a tangent is. Secant squared, good. Okay. Bring the power down, raise that to 1 power less, multiply by the derivative of what's inside. Do it over here. Bring the 2 down, raise this to 1 power less. And since it's now to the first power, I don't really need those parentheses. Now I'm taking the derivative of the inside, I get the tangent. You told me the derivative of a tangent was a secant squared. We keep the angle the same until the very last step. Now we go inside there and take the derivative of the 3x plus 5. Not much simplifying. You could probably put the 2 with the 3 together and make a 6 out front. So that's not worth rewriting that whole line for. Did this make you think of any homework problems you wanted me to work now? Not there yet. Saving them for the weekend. You don't want that social life to get in your way. Okay, so I'm trusting that this makes sense for you, because now we're going to start implicit differentiation. In this section, we're taking the derivative of functions. Y is equal to, f of x is equal to, and the other side just has expressions on x. But in implicit differentiation, we start with an equation. The x's and y's are mixed up, and it's not algebraically possible in most cases to write y explicitly as a function of x. But we're still interested in finding a y prime term, the change in y with respect to x, or the derivative of y. So let's work this out, and we'll get section 3.6 started. Maybe. Start here and work backwards. Try to spell differentiation. D-I-F-F. Different.
G-I-A-T-I-L.
D-I-A. Good God. That's a sign of aging. It happens to everybody. Just in the middle, but when I start falling down, it's time to retire, isn't it? Okay, so in this section, we will start with an equation. As opposed to a function. And in the equation, it's implied that y is a function of x. That x is the independent variable. and y is a function of x. And we're interested in finding the derivative of y with respect to x, which takes too long to write. Instead of writing that, I'll usually write y prime. But in the next section, we're going to do more implicit differentiation, where both our variables x and y are in fact functions of a third parameter, t. And we're going to be interested in finding the derivative of y with respect to t, and the derivative of x with respect to t. So keep in mind, when I write y prime, I'm reserving that for derivatives with respect to x. We take the derivative of each term in the equation. The chain rule applies wherever a y is involved. Chain rule applies to the y's. In other words, if I have something like y to a power, I bring the power down, raise the y to one power less, and then I multiply by y prime. If I have, for instance, the sine of y, I take the derivative of the sine function to get the cosine of y, then I take the derivative of the angle and get y prime. So if I take the derivative with respect to x of some function that involves a y, I get the ordinary derivative. I don't know how to do it. Put it with a power. So I'll just show you for the power. Bring the power down, raise the y to one power less, and then multiply by y prime. And the same is true for all of our other functions. Then we generate an equation that has both all three, x, y, and y prime in it. We algebraically solve that equation for y prime. Solve that for y prime. For instance, I wrote this down for y'all so that you don't have to spend so much time writing this stuff. But I'll still write it on the board. So my first equation, I'm asking you to find derivative of y with respect to x. And the equation in this case is 3 times x to the negative 2 plus the square root of y minus e to the y is equal to 1 over x. So can you see the difference between an equation and a function? That's the key to use implicit differentiation. I'm going to remove the square root sign and write that y to the 1/2 power. And I'm going to replace this and write that as x to the negative 1. And I'm going to leave a little gap in front of each term because I'm going to put in there in red and I'm taking the derivative of each term. So I'm just gonna recopy this equation. Leave a little gap right here. A little gap right here. And then here. So I set myself up so that I can use power rules everywhere. Then when I said take the derivative of each side of the equation, I can take the derivative of each term. Derivative of a sum is the sum of the derivatives. So this step is telling me I'm taking the derivative of that term. I'm going to take the derivative of that one, this one, and then that one. This step I'll hardly ever put in anymore. I just wanted to show you my thought process. The terms are separated to plus and minus on each side. The derivative of 3x to the negative 2 is just going to be negative 6x to the negative 3. X is the independent variable, so I don't have any chain reaction. But over here, y is a function. So like I said over here, I bring the power down, raise that to 1 power less, and then I multiply by the derivative of what's inside, whether I use the dy dx or the y prime notation. This will be the last time I use this notation because that takes a lot more time. Over here, derivative of x to the negative 1. Oops, sorry, I missed a term. The derivative of e to the y is itself times the derivative of the exponent. And then over here, the derivative of x to the negative 1 is minus x to the minus 2. So there's the step where I said we're going to get the equation that has our derivative term in it. And we're going to solve this equation for y prime. These are the only two terms that have the y prime on them, so I keep them here. I'm going to take this term and I'm going to add it to the other side. So I still have 1/2 y to the negative 1/2 times dy dx minus e to the y times dy dx. And now on the other side, I'm adding this over here. So I have 6x to the negative 3. And then waiting for me over there is minus x to the minus 2. Keeping the y prime terms together now allows me to do a factoring step. I'm trying to solve for y prime, so I'm going to pull that out. I don't care if there are other common factors. All I want is to isolate this. So factor out your y prime term. That's all that changes. This stays the same. And then we divide by the stuff that's in the parentheses. And we're done. We can use this to answer questions like if this graph had a tangent line somewhere, we can use this to find the slope of the tangent line. And I didn't simplify anything. I hope that doesn't disturb you. Some of you look disturbed. You understand the steps? Okay, let's do the other one together, and then I'm going to kind of catch you on your own. This is kind of fun. It's exactly the same kind of problem that we're doing in our Cal 3 class. We're just doing it with several variables. So you got to get the hang of it here. You'll see it again. So the second one, again, find the derivative. If you want to use y prime, you can, and I'm going to in this case. Find y prime if we have 6x squared times y cubed plus the tangent of y is equal to the sine of x. So again, you're noticing the equation as opposed to the function. But another thing you need to notice is that we've got a product going on right here. So for this term, make sure you use the product rule. Treat 6x squared as the first term and y cubed as the second term, and knock out your product rule right there. So I'm going to skip this step. We're doing this step in our head. We're taking the derivative of each term. Check if you got your product rule right. I'm going to do first times the derivative of the second plus the second times the derivative of the first. So my first is 6x squared. Now I'm taking the derivative of y cubed. That's a y to a power. You start by bringing the power down, raise that to 1 power less, but now you got to take the derivative of whatever function y is represented. Then the other way, copy down the second, which is the y cubed, and then take the derivative of the first term, and you just get 12x. X is the variable, the independent variable, so you don't get a version of an x prime. Right, y prime means the derivative of y with respect to x. So x prime would mean the derivative of x with respect to x. That's just one. All right, that takes care of that term. Are we okay with that? Is that the way you did it? Now we're here. We're taking the derivative of the tangent of y. Can somebody tell me what I get for that? Secant squared of y. That's the derivative of the tangent function. Now inside the parentheses, you've got a y. Its derivative is y prime. Across the equal sign, we take the derivative of the sine of x, get the cosine of x. How's that? That's the main part. Everybody good with that? If not, give me that look of bewilderment like, oh. Good. All right, I'm going to isolate my y prime terms. This one and that one. I'm going to put this to the other side, and I'm going to put it to the other side in alphabetical order. I'm going to subtract 12xy cubed. Put it over here. There's the cosine of x minus 12xy cubed. I'm going to put these together. I'm going to make that an 18x squared y prime. I'm going to put this in alphabetical order, make that, oops, I did that already. Oh, well, I'm okay, I'm just going to copy that last one down. Secant squared of y times y prime. Once you group them together, you factor out the common factor of y prime. So I think I got enough room to do that right up here. Pull out the y prime. So we rewrite this side without the y prime in it. 18x squared y squared. Plus the secant squared of y. And then this side as before. Cosine of x minus 12x y cubed. And then the last step is to divide by what's in the parentheses. So I get y prime is equal to the cosine of x minus 12xy cubed, all divided by the stuff in the parentheses. 18x squared, y squared, plus secant squared of y. Put a big old cloud on it. Show some artistic ability. That's a nice little cloud, isn't it? Can we try another? Over to here. Number 2 right here. Go all the way to the left. So pushing left makes it go right. Whoops. Not that for getting you seasick. There we go. So let's see, third one. Find y prime if you have x times the cosine of 4y minus y to the 5th is equal to 12 minus y. A whole bunch of y's in this one. So again, we're going to take the derivative of each term. This is one term, that's a term, that one is, and that one. So you have 4 terms here. What do you notice about the first term? Product rule. You got an x times the cosine of y. So do the product rule for the first one. And then the rest ones are just individual terms. Give you a minute to try it. Then I'll catch up with you. Make sure you read the first line right. Here comes the product rule. We get the first times the derivative of the second. So the first thing I see is a cosine. When I take the derivative of that, I get minus the sine of the same angle. Now I go inside and take the derivative of the angle. That's the 4y prime. So that's multiplied right there with the sine. That's the first times the derivative of the second. Now the other way. The second times the derivative of the first. The first is just an x, so its derivative is 1. I didn't ask you to get that. Now the derivative of y to the 5th. Take its ordinary derivative, 5y to the 4th, then indicate that we've taken the derivative of the y. Derivative of 12 is 0. What about that last term? What's its derivative? All right. Good. So let's see. I've got a y prime term here, here, and here. I'm going to move that to go with the other y prime terms. This is a non-y prime term. I'm gonna subtract that and put it on the other side. I'd also try to write this stuff without parentheses. So I'm going to write this as minus x sine of 4y. Whoa, let's put the 4 with the x. So how about minus 4x sine of 4y times y prime? That I moved over. Then I've got minus 5y to the 4th times y prime. That one's coming over as a plus y prime. This one's going over as a minus cosine of 4y. Write my little red arrow there. Put that arrow up here. Group them together on one side of the equal sign, so that in the next step we factor it out. So rewrite this line without the y prime. We have a minus 4x sine of 4y minus 5y to the 4th. What about when I factor out this y prime? Put a 1 right there. And then divide both sides by the junk in the parentheses and you're done. Y prime is minus the cosine of 4y divided by that big line. Minus 4x sine of 4y minus 5y to the 4th plus 1. So this is the important step, because after this step, it's all very routine. Everybody okay with getting the derivative in the first line? I need to back up and point anything else out? All right, so the next example, let's use our derivative to tell us about the slope of the tangent line, and then write the equation of the tangent line. Write an equation of the tangent line. To the curve x squared minus 4xy plus y cubed is equal to 6 at the point 5, 1. So from here, you know you need the derivative, but from here you see an equation, so you get the derivative between the steps we just did. Use implicit differentiation. Keep your eye trained to find where the product rule is. Does anybody see the product rule in here? And be careful not to lose that minus sign in front of the product. It goes on both terms in your product rule. Not going to get a pretty number for your slope. You can get 6/17 as the slope. Now, the neat thing about having a point is you can skip these steps here. If you're given the point, you can go ahead and insert the x and y right here, and then you have an easier equation to solve for y prime. But if you want the practice of doing that, no problem. Get 6/17 as your slope. Good. Get 6/17, my bet is you blew this sign right here in the product rule. So watch this step here, I'm gonna take the derivative. Derivative of x squared is just plain old 2x. Now I'm gonna take this minus sign, put it here in parentheses, and I'm gonna do the product rule where 4x is my first term and y is the second term. So we'll have first times the derivative of the second plus the second times the derivative of the first. Is that okay? Now I'm over here taking the derivative of y cubed. So we get 3y squared, back on the y prime. Cross the equal sign, the derivative of the constant is 0. So now I'm going to show you the shortcut. We've got a point, let's put 5 in for x, 1 in for y. So we're going to have 2 times 5 minus, I'm going to distribute the minus sign as I do that. So we'll have 4 times 5 times y prime minus 4 times y, but we know y is 1, plus 3 times 1 squared times y prime is equal to 0. That gets rid of all the pesky x's and y's and gives us nice numbers to work with. I have 10 minus 20y prime minus 4 plus 3y prime is equal to 0. We put together our like terms, minus 20y prime plus 3y prime is minus 17y prime. 10 minus 4 gives me a positive 6. And so I'm going to solve this for y prime. Let's just take this to the other side since it's negative. So we have 6 is equal to 17 times y prime, which says that y prime is 6/17. And as you know, that's the slope of the tangent line. To write the equation of the tangent line, we just fill in the point slope form. Y minus y1 is equal to m times x minus x1. There's my x1, y1, and there's my m. So y minus 1 is 6/17 times x minus 5. And it's not worth multiplying that out. So we can still use this stuff to find everything we did before. If this were some sort of graph with the position changing, we can figure out acceleration and velocity and stuff like that. But it also gives us a function of x and y. So we can find higher ordered derivatives as well. I don't want to take the derivative from here, because this one's a messy example. Let me give you an easier example, and then we'll try the one on the sheet. So let's look at how do we use implicit differentiation to find higher ordered derivatives. A little bit smaller. Y prime and y double prime in terms of x and y only. Let's start with the equation. Cosine of x plus the sine of y equals 3x. So your trained eye sees an equation, that's when you know to use implicit differentiation. We're going to start the same way. We're going to go through and take the derivative of each term, generate an equation that has x, y, and y prime in it, and solve for y prime. So I'm going to take the derivative of the cosine of x, and I get minus the sine of x. So differentiate each term. Minus the sine of x. Now I'm taking the derivative of the sine of y, and I get plus the cosine of y, but now I have to multiply that by y prime. And over here I get 3. We're going to solve for this term. So I'm going to add sine of x to both sides. And then I'm going to divide by the cosine of y. Oops, it's just y prime. We get 3 plus the sine of x divided by the cosine of y. I don't know, I need to include those parentheses. That deserves its own cloud. And here's how we get y double prime. The derivative of y prime is y double prime. So we'll take the derivative of both sides of this equation. We get the y double prime over here. Over here, we better use the quotient rule. So let me make some rules. That's going to take a bit. When we use the quotient rule, we're going to get an expression on the right-hand side that has x, y, and y prime in it. So we'll have to put an additional step to get rid of the y prime. So we're going to do the quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So the derivative over here is where the y double prime comes from. Here comes the quotient rule. My bottom is the cosine of y. Now the derivative of the top. What's the derivative? 3 plus the sine of x. The cosine of x. Minus the top, 3 plus the sine of x, times the derivative of the bottom. Your turn. What's the derivative of the cosine of y? Negative sine of y times y prime. All over the bottom squared. I'll just write it like that. To simplify this, I'm going to take this minus sign, put it with that one, and make that a plus sign. I can't combine these because they have different angles. So I'm just going to rewrite it without parentheses. Cosine of y times the cosine of x. Remember again, this one does not cancel with that one because it's not a common factor. There's not a cosine of y over here. So there's my first term. This minus sign, but the other one gives me a plus here. I'm going to keep it factored. I'm gonna leave a gap where the y prime was. Because I know what y prime is in terms of x and y. It's sitting over here in this cloud. Instead of putting y prime over there, we're gonna put this fraction over there. Because I want everything in terms of x and y only. So put this in where the y prime is, right here. That'll be 3 plus sine of x divided by the cosine of y. You get a big old mess. Well, make sure you understand where that big old mess came from. You want to watch me clean it up? You can leave your problem right there. But I'm going to clean it up in case some weirdo says, hey, why don't you find y triple prime? I wouldn't want to take the third derivative from here. I'm not going to take the third derivative because it doesn't clean up a heck of a lot. The first thing I'm going to notice is that if I multiply this with that, I get 3 plus the sine of x all squared. The next thing I'm going to do is get rid of this. I'm multiplying this whole top row by the cosine of y. Whatever I do to the top, I have to do to the bottom. So I'm going to multiply all of this by the cosine of y, which means I have to do it down here as well. So I got to distribute it through the plus sign. When I multiply this by the cosine of y, I get the cosine squared of y times the cosine of x. When I multiply here, it cancels. So I'm going to get this factor squared times the sine of y. There's the squared from multiplying those two like factors together. There's the sine of y. And then down on the bottom, I'm going to have cosine cubed. And that's as far as you can simplify it. There's really no need to multiply anything out because it's unpleasant and it doesn't get any smaller. Okay? All right, you've got one on your sheet. See if you can find the second derivative on problem number 5. Only in terms of x and y. So that's what this notation means, d squared y over dx squared. It's the same as y double prime. And your equation is much prettier. X squared minus 2y to the 4th is equal to 10. You just have 3 terms there. Take the derivative of each term and get an equation for y prime. Solve for y prime, then start from there to get y double prime. I will not learn how to drive this stupid thing. Don't want me in there. Put a little box or something around your expression for y prime, because you're going to need to find it at the end to substitute out the y prime in your second term. We'll simplify it together. Still don't trust you driving the car by yourself. Try simplifying it. Once you have your y prime, take the derivative from there. Everybody got the y prime yet? Catch up with you. Just have three terms to take the derivative of. The derivative of x squared is 2x. Here's where the chain rule comes in. The derivative of 2y to the fourth. 4 knocks with the 2 to give me the 8. Y to the third. Y prime. Don't screw it up here. Derivative of 10 is still 0. So to get the y prime by itself, I subtract 2x, divide by the negative 8y cubed. Can I do that in one step? Will you allow that? I subtract 2x, divide by negative 8y cubed, and that's my y prime. And I'm going to simplify it. The two negatives give me a positive. 2 goes into 8 4 times. So I have y prime is equal to a positive x over 4y cubed. Any questions to there? So you know you're going to need the second derivative using the quotient rule. So try that now. This y double prime comes from taking the derivative of this, right? Now I put the bottom term here, that's 4y to the fourth. The derivative of the top, it's just 1, right? I don't have to put anything here. Minus the top. Now the derivative of the bottom. Did you get 12y squared y prime? All over the bottom squared. Now I'm going to take this y prime out. And I'm going to put that expression on the right-hand side here, right where that y prime is. And I'm going to clean this up a bit. Okay, y double prime is equal to 4y to the fourth. This I'm going to put in alphabetical order as minus 12 xy squared. Out comes the y prime. In goes x over 4y cubed. And then remember, if you square this, you square both terms. So I get a 16y to the sixth. Were you able to get it to there? Yes.
Why is the y cubed?
Did I screw that up? Why is the y cubed here?
I'm not cubed, sorry, the fourth.
I don't know. That's my bad, right? Because I can't see that far. That better? Is that my only mistake? Can I get partial credit?
Yes.
I don't need it. I have my degree. Partial credit does me absolutely no good. Okay, you can leave it there. I'm gonna clean it up. I'm a trained professional. What I'm going to do is I'm gonna put this x with that one. I'm gonna take that 4 divided into the 12, give me a 3 here. And I'm gonna cancel a y squared with a y cubed and leave me a y down here. So I have 4y cubed minus, what I say, 4 goes into 12 3 times. This x times that x gives me x squared. Y squared cancels with two of these, leaves me a y on the bottom. And downstairs I have 16y to the 6th. What can I do to get rid of this y? Multiply top and bottom by y. So to multiply by a red y. Clean that y up, multiply top and bottom by y. So I can distribute that, that's where the y to the 4th will come from. That one cancels, so I have minus 3x squared. And I have 16y to the 7th on the bottom. So this one's not as wacky. You could possibly find a third derivative. We're not going to. We have more important things to learn.
Oh, never mind.
We're feeling creative right there. Okay, we're going to take a break from the handout of example problems, and we're going to use the idea of implicit differentiation to generate formulas for our 6 inverse trig functions. Inverse sine, inverse cosine, inverse tangent, inverse secant, inverse cosecant, inverse cotangent. So you're going to get 6 new formulas. But the good news is you only need to remember 3 of them. The other 3 are redundant. You'll see why in a second. Then we're going to use that same concept in implicit differentiation to derive formulas for not just things like e to a power, but maybe something like 10 to a power. Now, the steps that I do to derive these formulas are good to know, because if you ever forget the formula for the derivative of any of the inverse trig functions, they're really easy to replicate. Okay, so we're going to derive formulas for the derivatives of each inverse trig function. And remember how we defined our inverse trig functions. We said the inverse sine of an angle or of a number is an angle that we take the sine of to get that number. So whether I use this inverse notation or arc sine notation, the arc sine of a number x, where x is a number between 1 and -1, is an angle between negative pi over 2 and pi over 2 that I take the sine of to get that angle, to get that number. I don't know how to take the derivative over here, but I do know how to take the derivative over there. So to get y prime, I start from here and take the derivative of both sides. What's the derivative of the sine of y? That's where the implicit differentiation comes in. And then the derivative of x is 1. And when I solve for y prime, I get 1 over the cosine of y. Well, if I want to know a formula for the derivative of the inverse sine of x, it would be kind of handy to have that derivative as a function of x. So I'm not going to stop here. I'm now going to write this expression on the right as a function of x. And here's how. This line describes the behavior of sides of a right triangle of an acute angle y. So here's a picture described by this. Let's put the acute angle down here. The sign describes which 2 sides of this right triangle. The opposite over the hypotenuse. So think of this x as x over 1. And that means I can make this side length x and that side length 1. Now we're going to try to find the cosine of that angle y, and that involves the adjacent side. So let's put a letter right here for now and use the Pythagorean theorem and get the expression for that letter as a function of x. This picture says that leg squared plus leg squared is hypotenuse squared. And I'm trying to find b in terms of x, so I'm going to subtract x squared from both sides, and then I'm going to take the square root of that. And I'll take the positive square root as I drew that in the first quadrant. So now I'm going to replace that b with the square root of 1 minus x squared, and now I'm going to put that in down here. Here's angle y. The cosine of that angle is adjacent divided by the hypotenuse. The hypotenuse just is length 1, so all I need to do is put the adjacent side down here. That, men and women, is the derivative of the inverse sine of x. The derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. I'm going to put that on the far right-hand side. So that's our first formula. Derivative with respect to x of the inverse sine of x is 1 over the square root of 1 minus x squared. Now let's do all of this again using an inverse cosine. So I'm going to start by saying the inverse cosine of a number between 1 and -1 is an angle between 0 and pi if and only if the cosine of that angle gives us back that number. Now we take the derivative of both sides of this equation. The derivative of the cosine of y is minus the sine of y. Now I take the derivative of the angle and get the y prime. On the right-hand side, the derivative of x is 1. And so I have y prime is equal to 1 over the negative sine of y. Let me put the negative right here. Let's make the right triangle that goes with this picture. This picture says that in this right triangle, with this acute angle y, the cosine of y is x. The cosine is the adjacent over the hypotenuse. So this time my x lands here, and the 1 goes as the hypotenuse. We do the same steps to find the length of this side, and this is what you'll get again. But this time it's over here. So using that picture, the sine of that angle y is this side over 1. So look at the derivative of the inverse cosine. It looks just like that, but with a negative sign on it. That's going to happen again and again. Once we get the derivative of the inverse tangent, it'll look the same as the derivative of the inverse cotangent, only it'll be negative. The derivative of the inverse secant is the same as the derivative of the inverse cosecant, but the derivative of the inverse cosecant is negative. Again, any of our inverse trig functions that involve the letter c are going to have the minus sign. Easy to remember. So I'm only going to get you the next two. Put an inverse tangent right here. Do that one next. So that makes that a tangent. We can do this real quick, so let's do it real quick. What's the derivative of tangent? So the derivative up here gives me secant squared of y times y prime. The derivative of x is 1. So y prime is going to be 1 over the secant squared of y. Now my picture. Put the acute angle y down here again. The tangent represents opposite over adjacent. So if you think of this x as x over 1, my opposite side has length x, my adjacent side has length 1. The hypotenuse then satisfies leg squared plus leg squared is hypotenuse squared. So here's leg squared plus leg squared. And then that would have a square root sign on it. Leg squared plus leg squared is hypotenuse squared. The secant represents, well, let's see, cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. So if I take hypotenuse over adjacent, I just get that. Here I've got a secant squared. So I get that thing squared, which kills the square root sign. So when I put that in here, you get our derivative of the inverse tangent, 1 over 1 plus x squared. Again? You know what I got? Right, leg squared plus leg squared is hypotenuse squared. And then when I square that here, I lose the radical sign. So add that to our list. The derivative with respect to x of the inverse tangent of x is 1 over 1 plus x squared. And just to make things nice, the derivative of the inverse cotangent is a negative 1 over 1 plus x squared. I do have time to do the next one, which will be the inverse secant. So we start with our definition. The inverse secant of a number x is an angle y if and only if I take the secant of that angle y to get us x. This is what we take the derivative of using implicit differentiation. What's the derivative of a secant? Secant tangent. So over here I get secant y, tangent y, and now the implicit differentiation step, the y prime. Derivative on the x is just 1. So y prime is 1 over secant y, tangent y. I know that the secant of y is x. So that's going to just be an x. We'll draw the right triangle to get the tangent of y. So from here, put the angle y here. Secant is hypotenuse over adjacent. So my hypotenuse is x, my adjacent is 1. I got to figure out this length. So that 1 squared plus that length squared gives me x squared. Can you tell me what that's going to be? Correct. From that picture, the tangent is opposite over adjacent. So now let's fill that in. Y prime is 1 over, the secant of y is just x. The tangent of y is that side over that side, but that's just a 1. So I have this right here. Okay, there's the derivative of the inverse secant. So let's see if I can put it on here. Derivative with respect to x of the inverse secant of x is 1 over x times the square root of x squared minus 1. And the derivative with respect to x of the inverse cosecant looks like that, but with a negative 1 on it. Now, there's a small disclaimer here. Our inverse secant was a wacky kind of function. We had to cut it off in certain values, where that number x sometimes could be negative. When I drew this right triangle, I drew it so that that number x was always positive. To solve that issue, we typically see this x right here in absolute value bars. We don't have to worry about the absolute value here because that's positive anyway. So to make this agree with the domain of these guys, you'll see the absolute value bars on there. I get sloppy sometimes and leave it off, but that's me. You put it on. All right, then there's chain rule versions of this. We'll go over some examples with that. And I've got some more to do in this section because it's a really long section. So I'm just about 2/3 of the way through with section 3.6. All right, you guys have a marvelous weekend.